In this system of differential equations, system in the sense that we've got some vector function and a coefficient matrix times that vector function tells you the derivative of the vector function. If we want to solve this, first of all, the problem does mention sketching out a phase plane. Have you seen what a phase plane is yet? The idea of kind of like a direction field, but for systems of differential equations. So if we wanted to sketch out the phase plane, before we even solve the differential equation, we can get a sketch of what the solution should look like. If you think of vector x as a set of xy coordinates, so we've got an x-axis and a y-axis, or you could call them x1 and x2, whatever variables you want. But if we rewrite this differential equation, the matrix differential equation, as two separate scalar differential equations, we could say, if this is dx dt and dy dt, we could say dx dt equals multiplying these together. So 2x minus 1y. And then multiplying this row and this column, 3x minus 2y. So just standard matrix multiplication, multiplying this matrix by this vector and setting it equal to the derivative of this vector. So if we think of the x vector as a vector of two functions, x and y, we can say dx dt is 2x minus y and dy dt is 3x minus 2y. And if we wanted to turn that into essentially a direction field, like the ones we were looking at way back at the beginning of the quarter, how do we turn dy dt and dx dt into the slope, dy dx? Is there any way we could combine these to get just dy dx? We want something about dy divided by something about dx, how fast y is changing divided by how fast x is changing. And we have something about how fast y is changing and something about how fast x is changing. What we can do is just divide these. dy dt divided by dx dt. That's how fast y is changing divided by how fast x is changing. And algebraically, you can think of that as the dt's canceling out, so you just get dy over dx. So if we fill that in, we get dy dt over dx dt. So what we now have is a formula describing the slope, the dy over dx slope at any xy location, xy coordinate pair. So what we could do here is we could start drawing out slopes based on that formula. So let's try this, try writing the slope at a few points and see what we get. We know dy over dx equals 3x minus 2y over 2x minus y. This is essentially our original differential equation combined and written in terms of just x and y without any time dependence at all. So if we start filling in some values here, let me mark some actual points on that graph here. Let's say 1, 2, 3, -1, -2, -3. What happens if we try the origin, if we plug in 0 for x and 0 for y? Yeah, it's kind of undefined. The slope is going to be undefined. So it's not truly a discontinuity though, because if we go back to the originals here, we can fill in 0 for x and 0 for y. If we go back to these originals, what happens if x is 0 and y is 0? If x is 0 and y is 0, how fast is x changing and how fast is y changing? Yeah, both of those derivatives are 0. which means if the location we're starting at is the origin, it's just going to stay there forever. So this point doesn't really have a slope because if you're at that point, you're not moving as time passes, you just stay there forever. And what do we call that? If you go back to the language we were using at the beginning of the quarter with direction fields, what do we call it if you're at some location and you just stay there forever because the derivative is 0? If you think back to scalar equations for a moment, let's say you had an equation like dy dt equals y times 5 minus y. And you notice, oh, wait, when we plug in 5 for y, this becomes 0. So if you start off at 5, you stay there, you stay at 5 forever. What would we call y equals 5 then? It is a constant function, but more specifically, we call that equilibrium. Then we'd say y equals 5 would be an equilibrium solution in the sense that it's a value that if it's that value, you just stay there forever. Likewise, y equals 0 would also be equilibrium in this differential equation. But we would probably want to also figure out what kind of equilibrium. Is it stable equilibrium or unstable equilibrium or semi-stable? Same idea here. At this location, if you're at x equals 0, y equals 0, both of these derivatives become 0. So that means if you start off with your initial conditions at 0, 0, you just stay there forever. That is an equilibrium location. But we'd want to figure out what kind of equilibrium, and we can do that by analyzing other points nearby. So if we try, for instance, let's say we keep y being 0. In fact, if y is 0, then no matter what x is, what does this turn into? Yeah, 3/2. So in general, if y equals 0, then dy dx is positive 3/2. So everywhere on the x-axis, everywhere where y is 0, we should expect x to be exactly 3/2. In other words, a slope of 1.5. So maybe up 3 over 2 would be some slope kind of like this. So we know what the slope is everywhere on the x-axis. But because time matters here, we want to be a little more specific. By writing it as dy over dx, we're ignoring time. But since time is playing a role in the original differential equations, we should consider what's happening as time passes. Like this slope of 3/2 might mean you're going up and to the right as time passes, or it might mean you're going down and to the left as time passes. So to check that, we should look into what's going on when y is 0. When y is 0, would you say x and y are increasing or decreasing as time passes? Or does it depend on something else? Because we'd have x prime is 2x and y prime is 3x. So would those be positive or negative values? Is 2x positive or negative? And is 3x positive or negative? It could be positive, but what does it depend on? Yeah, exactly. It depends on the value of x. So if x is positive, then both of these derivatives are positive. So we're going up and to the right. So we should really attach little arrows to these, not just lines. But if x is negative, then both of these will be negative. So we're decreasing y and decreasing x, going down and to the left. So these should all be little arrows. We've got up and to the right on the right side and down and to the left on the left side. So we at least know what the direction arrows, the phase plane arrows look like on the right side and the left side. We can also check above and below the origin by setting, how would we deal with any point on the y-axis? Yeah, we could set x equal to 0. We could say if x equals 0, then dy over dx equals, what does this reduce to if x is 0? Yeah, it's going to be 2. So every point on the y-axis is going to have slope 2. So positive slope and a little bit steeper than these ones. And again, we could get more precision figuring out which direction. Is it up and to the right or down and to the left by checking these original differential equations. Again, plugging in 0 for x, we get x prime equals negative y and y prime equals negative 2y. So what's going to determine whether these give you positive or negative slopes or positive or negative directions of travel? What would happen to these values, for instance, these derivatives, if y is a positive value? Yeah, if y is positive, then y prime is negative, so y is decreasing. And also x prime is negative, so x is decreasing. So for any positive value of y, these derivatives are negative, so we have downhill, down and to the left. Whereas if y is a negative value, both of these derivatives will be positive. So for any negative y value, we get an upwards trend, up and to the right. So we now have at least these direction arrows everywhere on both axes. Any questions on that phase line or phase plane so far? And notice that this is very similar to the phase line we were looking at back in the autonomous first order equations. We're just making it more complex by adding an extra dimension. Now that we've got the axes, let's try some in-between values as well. Probably we want at least 1 in each quadrant. For example, what if we said, let's say 2, 2. If you set x equal to 2 and y equal to 2, what does this turn into if x is 2 and y is 2? If we fill in 2 for x and 2 for y, that's what? 6 minus 4 over 4 minus 2. So yeah, 2 over 2, that'll be 1. So that means at 2, 2, the slope is going to be exactly 1. And again, that leaves us with the question of, is it up and to the right or down and to the left? So we can check each of these individually. We're going to get dx dt is 4 minus 2, so that's 2. 6 minus 4, so that's 2. These are both positive, so that's up and to the right. And then we might try, for instance, maybe x equals 2, y equals negative 2 to get something in this quadrant. And if we fill that in, we're going to get 4 plus 2, so that's 6, and 6 plus 4, so that's 10. So 10 over 6, 5/3. So at this point, the slope is positive 5/3. Also, since these are both positive, that's also going to be up and to the right. And then we could likewise try these 2 points maybe, again, to get some more detail. So we've got, let's say, negative 2, 2. If we run the calculations on those, we've got negative 4 minus 2, so that's negative 6. And negative 6 minus 4, so that's negative 10. So that'll be the same slope in terms of 10 over 6, 5/3. So here we've got the same 5/3 slope. But since these are both negative, which direction is that going? Yeah, down and to the left. And we could run the same thing here if we make these both negative. X equals negative 2, y equals negative 2. Nothing particularly special about these points. It's just a good idea to try several points and get an idea of what's going on in each quadrant at least. So x equals -2, y equals -2, we get -4 plus 2 and -6 plus 4. So the slope is going to be 1, -2 over -2. But again, these are both negative, so that's down and to the left. So it looks like we've at least got sort of a general trend. We might even be able to sketch in a few sample solutions. It's kind of difficult without more data points. We could always graph more data points by filling in more x and y values. But it looks like we can at least say these seem to be trending kind of like this and kind of like this, probably with some curvature because it's more steep on the y-axis and less steep on the x-axis. So I'm thinking curving kind of like this. But it looks like there's some sort of discrepancy here because we definitely seem to have a curve like this going up and to the right. And then we've also got curves that seem to be going down and to the left. Presumably somewhere in between, there's sort of a split. Somewhere in between, we're going to split between, are we going up and to the right or are we going down and to the left? So we might want to add in more data points, get some more detail about what's going on in here. But we at least seem to have a general idea of the trend here. A rough sketch of the phase plane and a general idea of what some of the solutions are going to look like, depending, of course, on the initial conditions. Any questions on that phase line or phase plane so far? So that gives us a general idea of what kind of solutions to expect. Looks like most of these are coming in from some infinitely far away, passing by the equilibrium solution, and then shooting off to some other infinity. So it doesn't really look like most of these are converging to equilibrium. Everything seems to be diverging away from equilibrium, maybe coming in towards equilibrium for a while, but then shooting off to some other infinity. And if we wanted to check that, of course, we'd want to solve this differential equation. So let's try actually solving this, now that we've got a rough idea of what kind of solutions to expect. In general, if you've got a differential equation of the form x prime equals ax, what do we typically expect the solutions to look like? What's our usual expected format? What would be useful as a guess? Or if we back up to a scalar equation, let's say you just have like y, or let's say dy dt equals some constant times y. Because this is pretty comparable here, I think, that we have a derivative of y equals some constant scalar times y versus derivative of vector function x equals some constant matrix times vector function x. So it's kind of the same format of equation. It's just a vector function and a matrix multiplier as opposed to a scalar function and a scalar multiplier. And what would you expect the solution to this differential equation to look like? Or how would you solve this differential equation? Yeah, this should be e to the t, and not just e to the 1t, but e to the what? Yeah, it's going to end up being e to the rt. And also possibly times a constant multiplier. So the general solution to, because we want all possible solutions, the general solution to this is going to be e to the something t times a constant multiplier. We can make a similar assumption here, just based on the fact that this is the same format of differential equation, just with different kinds of variables. We can make a similar guess. If we guess that vector function x is e to the rt times c, although in this case, we want this to be a vector function. So we should assume that this constant is not just a constant scalar, but a constant vector. So this would be a reasonable guess based on what we expect from the equivalent scalar equation. And how would we check to make sure that guess works and figure out what has to be true about it to make it work? In general, how do you check if a function really is a solution of a differential equation? For instance, going back to this one, if I'm claiming that e to the RT is a solution, how would you check to make sure it really is a solution? Not just plug in some numbers, because the solution isn't a number, the solution is supposed to be a function. So how would you check if that function really is a solution to the differential equation? Yeah, substitute the function itself back into the original differential equation. Which of course means we'll also need the derivative of our guess because there's a derivative in the equation. So dy dt, what's the derivative of e to the RT? Yeah, r times e to the RT. So if we substitute this derivative, oh, and we also need a times c, because that constant multiplier doesn't change. If we take our derivative and substitute in for dy dt, and if we take the guess itself and substitute it for y, then we can see that it really is true that dy dt, r e to the RTC, is equal to r times e to the RTC. So that means since this guess makes the differential equation true, that means that guess really is a solution. Any questions on that so far? So let's try the same thing with the matrix differential equation. If we're guessing that vector x function equals e to the RT times some unknown vector c, we would check by taking the derivative of our guess first. Again, e to the RT just becomes r e to the RT when we take the derivative due to the chain rule. And we still have times this constant vector multiplier. To verify that, we would plug this into the original differential equation again and figure out what has to, well, first of all, if it even makes sense. And second, what has to be true to make it work. So if we try this, x prime, that's r e to the RT times c. That has to equal, or really we're checking, does it equal a times our guess? So we want to know, is it true, or is at least, is it possible for our derivative to equal a times our guess? And this at least seems reasonable. I mean, if you multiply r e to the RT times c, you get a vector that is composed of exponential functions. And if you multiply matrix A times C and then multiply by e to the RT, you also get a vector composed of exponential functions. So both sides of this equation result in a vector function with exponential components. And to figure out, so it at least seems reasonable that these could be equal. But we also want to figure out what has to be true about R and C to make it equal. So to verify that, or to figure out more information, is there anything here we could get rid of to simplify the equation? Anything we can divide out or multiply out to make it cancel completely? Is it possible to divide by the C vector? How do you divide by a vector? Something you've got to be careful about when you're dealing with division. Like, let's say we've got the equation 5 times x equals 30. Typically, we would just say, solve this by dividing by x, or sorry, dividing by 5. But what does dividing by 5 really mean? Suppose all we knew how to do was multiply. Could you solve this by multiplying? Yeah, multiplying by 1/5. You would solve this equation by multiplying by 1/5. In other words, the inverse of 5. When we say divide both sides of the equation by 5, that's really just shorthand for saying multiply both sides by the inverse of 5, which we can do because 5 has an inverse. But if we had something like 0x equals 30, could you solve this by dividing both sides by 0? No, why not? When we say things like you can't divide by 0, why is that undefined? Why can't you divide by 0? Going back to multiplication, dividing by 0 would mean multiplying by what? What would you multiply by that acts like dividing by 0, or that dividing by 0 is shorthand for? Yeah, we'd have to multiply both sides by the inverse of 0. The reason that doesn't work is 0 is the one and only number that does not have an inverse. In general, division by something really means multiplication by its inverse. When we say you can't divide by something, that just means that thing doesn't have an inverse. And that's where we run into trouble with vectors. Dividing by a vector would mean multiplying by the inverse of that vector, and vectors don't have inverses. The only matrices that even have a chance of having inverses are matrices that are square, same height and width. A matrix is a vector, or sorry, a vector is a matrix that has any amount of height, but width 1. It's not a square matrix, so it can't possibly have an inverse. So any vector that's more than height 1 does not have an inverse, and therefore you can't divide by the vector. Similarly, we don't really talk about dividing by a matrix because most matrices do not have inverses. If a matrix does have an inverse, you can multiply by the inverse, and that's kind of like dividing. But we don't really use that language. We don't talk about dividing by a matrix because most matrices don't have inverses. So we just say multiply by the inverse if there is one. But a vector definitely does not have an inverse. So we can't get rid of these C vectors because they're not invertible. But what other thing can we get rid of? What else shows up on both sides that does have an inverse? Yeah, e to the RT does have a multiplicative inverse. I mean, we could think of it as dividing by e to the RT, but really we're multiplying by what? What's the multiplicative inverse of e to the RT? Or what multiplier would cancel it out? Logarithm is the inverse function, but we don't really need an inverse function here. We're not applying a function. Yeah, we just need to multiply by something that will cancel it out. So yeah, we could write that as multiplying by 1 over e to the RT, or we could even describe that as multiplying by e to the negative RT. So if we just multiply both sides by e to the negative RT, which we would usually just describe as dividing by e to the RT. It's just that that's shorthand for multiplying by the inverse of e to the RT, which is e to the negative RT. That way, e to the RT times e to the negative RT cancels out on both sides. And we're left with scalar R times vector C equals matrix A times vector C. And again, we can't get rid of the vector C because it doesn't have an inverse. And moreover, if we were able to get rid of it somehow, we'd end up with a scalar equals a matrix. And that doesn't make sense. You can't have a scalar equaling a matrix. But what we can conclude is that we now have some vector such that the matrix times the vector is exactly the same as the scalar times the vector. Think back to linear algebra. What do we call it when a matrix times a vector happens to equal a scalar times the same vector? Would it be more recognizable if I rewrote that vector as V and rewrote that scalar as lambda? Have you seen that before? Exactly. These are the eigenvectors. If we have a matrix times a vector and the result is a scalar times the same vector, like if you find that for purposes of this vector, multiplying by the matrix ends up just like multiplying by 3.5 or something, that vector is by definition an eigenvector. This is what it means to be an eigenvector of a matrix. That for purposes of that vector, the matrix acts like a single number. And because that's the end result we get from making this guess, that tells us, yes, this guess works, but only if R is an eigenvalue of the matrix and C is the eigenvector associated with it. So this gives us an idea of how to construct our guess. This guess will work, but to make it work, we need to find the eigenvalues and eigenvectors of this matrix. The eigenvalues will give us the exponential constants, the R values, and the eigenvectors will tell us these constant vectors. So for that reason, we usually write this as e to the lambda t times v. So this guess should work. We should expect the solutions to a differential equation like this, a system of differential equations. We should expect the solutions to look like x equals e to the power of eigenvalue times t times the eigenvector associated with that eigenvalue. Which means that what we'll need to do is find the eigenvalues and eigenvectors of this coefficient matrix. Any other questions on the algebra behind that so far? Excuse me. Then let's try finding the eigenvalues and eigenvectors. If we want to find the eigenvalues and eigenvectors of this matrix, of that coefficient matrix, how do we usually find the eigenvalues and eigenvectors? What's our typical process for that? If we're starting with the idea that A times V equals a scalar lambda times V. How would we go about finding the eigenvectors or finding the eigenvalues? The trace, and what do you mean by the trace of the matrix? So the diagonal values, and what do we do with those diagonal values? Right, subtract lambda, because ultimately if we want to solve AV equals lambda V, typically we would start by subtracting lambda V from both sides, so we at least get all the variables we care about to one side of the equation. Then since V shows up in both terms, we can factor that out. If we do factor out V though, what's left here? What do we get if we factor V out of that expression? A minus lambda. Except for one thing. A is a matrix, lambda is a scalar. You can't subtract a scalar from a matrix. But what matrix could we have here that wasn't even written in? What's a matrix you could always insert without changing anything? The identity matrix, yeah. If we write in times I, that is a matrix with ones on the main diagonal and zeros everywhere else, multiplying by I doesn't actually change anything. That way we have, when we factor out V, we now have a matrix minus a matrix. Lambda I would just be multiplying everything by lambda. So lambda 0, 0, lambda. So that way, A minus lambda I is the multiplier that turns V into the zero matrix, sorry, the zero vector. In fact, if you think of this as a matrix times a vector equals 0, what do we call that in linear algebra if we're trying to find all vectors that become 0 when multiplied by a matrix? What kind of subspace related to the matrix is that? All the vectors that turn, the space of all the vectors that turn into 0 when multiplied by the matrix? Right, that's the null space. When we're solving A minus lambda I times V equals 0, we're really finding the null space of A minus lambda I. In fact, that's really what the eigenvectors are. Finding the eigenvectors of a matrix really just means finding the null space of A minus lambda I. Of course, we'll need to know what lambda is. And note that we want to have many eigenvectors, because what's one vector that will always work? What's one V value that will always make this add up to or multiply to 0? Yeah, if the vector V is 0, 0, if it's the 0 vector, that's always true. So in the same way that the 0 vector is always a member of every null space. So V equals 0 always works. We would typically call that the trivial solution. Trivial in the sense that, yeah, it's true, but it doesn't give us any useful information. We want to know if there are any other vectors that work. And again, think back to linear algebra. What has to be true about the matrix in order for the null space to have more than just the 0 vector? What do we need to assume about this matrix to get more than just the trivial solution? It has an inverse. Let me just call this M for the moment. If M has an inverse, what could we do to solve for V? What could you do with that inverse to get V by itself here? Yeah, if we left multiply both sides by M inverse, with order being important because in matrix multiplication order matters, then M inverse times M cancels out to the identity matrix, so we just get I times V, which is just V. And what remains on the other side? What's M inverse times 0? Right, we get the 0 vector. So it looks like MV equals 0 leads to 0 being the only solution. Unless what? What has to be true in order to avoid this conclusion? How could we get, or what has to be true about the matrix to get any vectors other than just the 0 vector? Is there any way to avoid this conclusion, or does MV equals 0 have to lead to V equals 0? Well, specifically, what has to be true about the matrix in order to not get to V equals 0 is the only solution? It looks like if we can just multiply both sides by M inverse, then 0 is the only solution. So what has to be true about M in order to not get that? What were we assuming about M in the first place that led to this conclusion? Or why were we able to just multiply by M inverse? Does every matrix have an inverse? No. We could have an M matrix that doesn't have an inverse, and then this wouldn't work. In general, if M is invertible, then V equals 0 is the only solution to MV equals 0. So if we want the other way around, if we want this to have many solutions and not just the trivial solution, we need to assume that this matrix is non-invertible. So that's what we're going to have to do here. We're going to have to assume that A minus lambda I, this matrix multiplier here, is non-invertible. Because if it was invertible, we'd end up with 0 being the only solution. And what we care about is the non-zero solutions. Going back to our original guess, if V was 0, we just get X equals 0, and that's boring. That's just the equilibrium solution at the origin of our phase plane. So we want the non-zero solutions, which means we have to assume that the matrix A minus lambda I is non-invertible. So that's really the key to the whole idea of eigenvalues, that A minus lambda I has to be non-invertible. In other words, since lambda is not yet known, we want lambda values that make this non-invertible. So that's really the whole idea of an eigenvalue. We can find an eigenvalue by finding values that make A minus lambda I non-invertible. And what's usually the fastest way to check if a matrix is invertible or not? Yeah, this is where the determinant idea comes in. If we want a matrix to be non-invertible, we need its determinant to be 0. Because if the determinant is anything other than 0, then that means the matrix is invertible. So we have to assume that the determinant of A minus lambda I happens to be exactly 0. That will guarantee that A minus lambda I does not have an inverse at all, which is the only way to open up the possibility of any non-trivial solutions for V, any non-zero eigenvectors. So that's the assumption we're going to have to make. So let's try that out. If we write out A minus lambda I, which is really just A minus lambda I, that is subtracting lambda from everything on the main diagonal, as we mentioned earlier. If we subtract lambda from everything on the main diagonal, we're going to get 2 minus lambda, -1, 3, -2 minus lambda. We want to take the determinant of that and set it equal to 0. That will guarantee that this matrix is not invertible, and therefore there are V values other than 0 that will work. And in fact, for finding the eigenvalues, we usually just start here. These steps are useful for showing why it works, or if you forget the formula in general. In fact, for anything you want to prove about eigenvalues or eigenvectors, if you want to prove that eigenvectors have to have some property or have some certain behavior, this is generally a good place to start. You can always start from the definition and then work from there algebraically. But in the sense of finding what the eigenvalues are, we're always going to be going through this process without even writing it down. You can just jump directly to this fact. You can assume that the determinant of A minus lambda I must equal 0. And that should give us an equation we can solve for lambda. Any questions on the theory of that so far? So let's try actually solving this equation. How would you write out this determinant? What would that determinant turn into when we simplify it? Or how would you evaluate a 2x2 determinant? Yeah, AD minus BC, the diagonals multiplied and subtracted. So multiply this diagonal, 2 minus lambda times -2 minus lambda. And separately multiply this diagonal, 3 times -1. Subtract those. And that determinant has to equal 0. And multiplying this out, we get 2 times -2, +2 lambda and -2 lambda cancel out. So we just have minus lambda lambda, so plus lambda squared. And then we've also got a minus 3 times -1, so that'll be +3. Simplifying that, we've got lambda squared minus 1 equals 0. This lambda squared minus 1 is what we would call the characteristic quadratic, in the sense that it's a quadratic that tells us everything we need to know about the eigenvalue. It's characteristic of the matrix. And how would we solve this for lambda? What would be a good way to solve this quadratic? In this case, yeah, since there's no lambda term, there's just a lambda squared term and a constant, we could just add 1 to both sides. And then what? Square it. So we get lambda to the 4th equals 1 squared, which is 1. Yeah, square root should do it. If we take the square root of both sides, yeah, square root. So lambda equals, and what's the square root of 1? Yeah, we do want to include both square roots, positive 1 and negative 1, because we're looking for all possible solutions to this equation. We want all eigenvalues. So we have 2 eigenvalues here, 1 and negative 1. Alternatively, what's another way you could solve this other than add 1 to both sides and take the square root? What else often works for quadratics? Yeah, this one happens to be factorable. In fact, any quadratic that has rational solutions, doesn't even have to be whole numbers. As long as the solutions are rational, then it should be factorable. In this case, it should factor to lambda plus 1 times lambda minus 1. And then we could say lambda has to be negative 1 or positive 1. So we get the same solutions. Or if it's not factorable, or even if it might be factorable, but looks like it's going to be too much trouble, you can always use completing the square or the quadratic formula instead. So any quadratic should be solvable. Worst case scenario, use the quadratic formula, and you'll end up with either 2 real solutions, or possibly just 1 real solution if it's a repeated root sort of thing, or possibly 2 complex conjugate solutions. But those are really the only options. 2 real eigenvalues, 1 real eigenvalue that's a repeated root, or 2 complex conjugate eigenvalues. In this case, we get real values. So let me make a note of that up here. We've got eigenvalues. Let's say lambda 1 is positive 1 and lambda 2 is negative 1. Doesn't really matter which one we call lambda 1 and which one we call lambda 2. We just choose an order for notation. Any questions on finding those eigenvalues so far? And what roles do the eigenvalues play in the solution, the guess we're going for? Where would the eigenvalue actually go in this guess? Yeah, we fill that in for lambda, which is in the exponent. So that means our solutions are going to be of the form, we're going to have 2 of them. We're going to have e to the positive 1t times some vector, let's say v1, and also e to the negative 1t times some other vector v2. And before we even find v1 and v2, the eigenvectors, what can we say about the behavior of these? What happens to each of these as t gets larger and larger as time passes? That is, what happens to e to the t as time goes on, and what happens to e to the negative t as time goes on? What are the limits of those? Specifically, which one? In terms of as t goes, yeah, we could think of this as limit as t approaches infinity. What happens to each one of these as t approaches infinity? If we've got e to the negative t versus e to the positive t. Which one specifically? I think we're going to have one of each, because we've got an e to the positive t and e to the negative t. E to the negative t, as t gets larger and larger, you get e to more and more negative exponents. What happens to like e to the negative 1,000 or e to the negative 1,000,000? What's that approaching? Yeah, e to the negative t approaches 0. It's going to get closer and closer to 0. And note that that's not just approaching the x-axis on a graph. That's a vector that's being multiplied by a smaller and smaller value. So that's some vector that's shrinking towards 0. Whereas here we've got e to the positive t times a vector. What happens to e to the t as t approaches infinity? What's the limit of that? Yeah, e to the positive t goes to infinity. And again, that's not an exponential growth curve. That's exponential growth times a vector. So we've got a vector in some direction that's growing larger and larger and larger, exponentially approaching outwards to infinity. So that suggests that there are some solutions that approach the origin, getting smaller and smaller, closer and closer to the origin as time goes on, and other solutions that just keep growing larger and larger outwards from the origin as time goes on. And this ties back into our phase plane. We were noticing we had curves that were shooting off to infinity. Those correspond to this exponential growth, e to the t times some vector. Any questions on the eigenvalue and their behavior it creates so far? Now that we've got those eigenvalues, then let's see if we can find the eigenvectors. Because we got the eigenvalues, next we need to find the eigenvectors. And for that, we could go back to, if we backtrack, because so far we were just looking at lambda values. If we backtrack, the last time we saw eigenvector, the v, was here. So we don't need to go back all the way to the beginning. We just need to backtrack to the last time we saw the eigenvector. If we write out this equation, a minus lambda I, now that we know lambda, times v equals 0, at this point, it's just finding the null space of a minus lambda I. So let's try writing that out. We want a minus lambda I times v equals 0. And we know the eigenvalues. Let's say we're using positive 1 as lambda value, lambda 1. Knowing lambda, how would you solve for the null space? How would you solve a matrix times a vector equals 0? Keeping in mind that this is non-invertible. So what's the other way to solve a matrix equation like this? If you're in linear algebra and you have a matrix times a vector equals 0, and you want to solve for that vector, but you know the matrix is non-invertible, what other approach could you use to solve that system? Do you remember the idea of an augmented matrix in row reduction? If we write out that matrix attached to or augmented with that single column vector, if we can write out the matrix of coefficients augmented with the vector on the other side of the equation, in this case, just the 0 vector, we should be able to row reduce that to find the solution. So let's try that linear algebra approach. We're going to augment a minus lambda I using a specific lambda value, augmented with the 0 vector, and then row reduce. In particular, let's try the first eigenvalue, lambda equals 1. So we're going to write out a minus lambda I. That is, we're subtracting lambda from everything on the main diagonal. Augmented with the 0 vector. And in this case, we're specifically using 1 for lambda. So every lambda we can replace with 1. 2 minus 1, negative 1, 3, negative 2 minus 1. And we're going to row reduce this. But when we row reduce, what's going to happen here? What row operation could you use to simplify this to row reduced echelon form? it might help to go back to the idea of pivots. If we look for the pivot in the first row, that is the first non-zero we encounter, this 1 is a pivot. It's the first non-zero in the row as you read from left to right. To make this reduced row echelon form, we need every pivot to be alone in its column. That means we need to get rid of this 3. What row operation would cancel out the 3? What multiple of 1 would get rid of the 3? That is, what could we add to the second row that would make this 3 cancel out? Yeah, if we add -3 times the first row, 3 gets a -3 added to it and cancels out. But then what happens to this -3? Yeah, that's also going to turn into, we're not multiplying it by -3 though. What are we adding to it? If we have a -3 and we're adding -3 times something from the first row, yeah, we're adding +3. So we got a -3, we add +3, what do we get? Right, that's going to turn into a 0 as well. So the end result of the row reduction is 1, -1, 0, 0, 0, 0. The second row cancels out entirely, because what do you notice about the second row as compared to the first row? Right, this is linear combinations. The second row is a linear combination of the first row, which in this case just means a multiple of it. If one of the rows is a linear combination of the other rows, then the rows are linearly dependent. So one of them is going to cancel out, which is the case because we were assuming from the start that A minus lambda I was non-invertible. If it's a non-invertible matrix, you should expect the rows to be linearly dependent, which means at least one of them is going to cancel out to all zeros, which we want because we want to have infinitely many solutions. We don't want it to be just one solution, which is the 0 vector. And now that we've got this written out in row reduced echelon form, we can find the solutions. Let's say we call our eigenvector, let's just call this AB for now, where A and B are some unknown numbers, the coefficients of the components of vector V, specifically V1. If we think of this as the A column and the B column, what does this row turn into as an equation? Or how would we write that row in the form of an equation? Yeah, 1A minus 1B equals 0. Then the second row would just be 0 equals 0, which is always true. So we don't need to worry about that. That just tells us the second row doesn't provide any further restrictions. But if A minus B equals 0, what does that tell you about A? Yeah, A equals B, which means we can treat, let's say we treat B as a free variable and A as equal to B. We can replace A with B and leave B as it is and say B could be anything. At this point, that suggests the eigenvector is anything of the form B, B, where B could be any real number. But we can simplify that further. Since B now shows up in every term, we can factor out B and what's left. Yeah, 1 and 1. So this tells us that the vector 1, 1 is an eigenvalue, an eigenvector. So 1, 1 is an eigenvector, and moreover, any scalar multiple of 1, 1 is also an eigenvector. So like -2, -2 is an eigenvector. 137.5, 137.5 is also an eigenvector. Any scalar multiple of 1, 1 is going to be an eigenvector. Specifically an eigenvector associated with lambda 1. So we're going to write this as V1 equals 1, 1. But keep in mind it's implied, even though we're not writing it out, it is implied that any scalar multiple of that is also an eigenvector. Any questions on that eigenvector so far? And let's find the other one as well. We can probably reuse some of our work here. We can go back to the augmented matrix except lambda 2 is -1. So 2 minus -1, -2 minus -1 becomes +1 instead. And that's going to be, so 2 plus 1, -1, 0. 3, -2 plus 1, 0. And I think in this case, it's even more clear that what's going to happen when we row reduce. If we've got a row that's not only a multiple of another row, but a row that's identical to another row, yeah, everything in that second row is going to cancel out anyway. So we can ignore that second row completely. You might want to at least, I mean, not necessarily write out, but at least think through what you'd have to do. If you specifically add negative row 1 to row 2, it'll cancel it out. But in general, you should expect at least one of the rows to cancel out when you're solving for the eigenvectors. If you don't get one of the rows canceling out, then that means something's gone wrong somewhere, and you should probably double check the eigenvalues. Because we want one of the rows to cancel out, so we get a non-zero, in fact, infinitely many non-zero eigenvectors. So if we fill that in here, using the same sort of approach, we've got 3, -1, 0, 0, 0, 0. If we rewrite this row as an equation, what do we get? Again, thinking of A and B as the variables, what would that row turn into as an equation? Yeah, 3 times A minus B equals 0. And you could solve this for either variable. There's not really, I mean, traditionally, we usually think of the column without a pivot as the free variable and solve for everything else in terms of that. But I think in this case, it's probably going to be easier to solve for B, just because then we don't have to deal with any fractions. B equals just 3A, just by adding B to both sides. So B has to equal 3A. If we write out V2 as AB, we could keep A as it is and replace B with 3A. Or alternatively, you could keep B as it is and replace A with 1/3 of B. Either way should work. In this case, if we now factor out A, what's left? Yeah, 1, 3. And again, any scalar multiple of that will also work. So like 10, 30 will work. -5, -15 will work. Any scalar multiple of 1, 3 will work. So that is our second eigenvector, the eigenvector associated with lambda 2. And by the way, how could you check your work here? Now that you find the eigenvalues and eigenvectors, how would you check, is that really the true eigenvalue and true eigenvector? Yeah, if we plug it back in, not necessarily to our guess, but to the definition of eigenvalues in the first place. Because the whole point of an eigenvalue is that, and an eigenvector is that the matrix times the vector should equal the scalar times the vector. So at this point, you could check by multiplying the original matrix times this vector, you should end up with 1 times the same vector. Likewise, multiply the original matrix times this vector, 1, 3, you should end up with -1 times the same vector. So try that out. Multiply this matrix times 1, 1, you should get 1, 1. Or multiply the original matrix times 1, 3, you should get -1, -3 as a result. Because the eigenvalue is -1, which means for purposes of this vector, the matrix acts like just multiplying by -1. Any questions on eigenvalues and eigenvectors? So let's try using that in our guess, because the whole point of all this, as far as the differential equation was concerned, is that the solution should look like e to the eigenvalue t times the eigenvector. So now that we have the eigenvalues and the matching eigenvectors, we can write out our guess in full with those values. So filling that in, we've got e to the eigenvalue t, so e to the 1t times the eigenvector 1, 1. And we also have e to the negative 1t times the eigenvector 1, 3. So each one of these individually, e to the t times 1, 1 and e to the negative t times 1, 3, each of those individually is a solution to the original differential equation. But if we want more solutions, first of all, what could you do to an eigenvector that will result in still another eigenvector? Because remember, 1, 1 is just one example of an eigenvector. What could you change to this and get? Yeah, you could multiply by any scalar. So let's say we multiply this by C1. C1 times 1, 1 is still an eigenvector. So C1 times 1, 1 times e to the t is still a solution. Likewise, 1, 3 could be multiplied by any scalar. So let's call this C2 times e to the negative t times 1, 3. Now we have infinitely many solutions and also infinitely many solutions. How could we combine those to get even more solutions? What were we doing back in chapter 3 with the second order equations? If you got like y1 and y2, yeah, you can add those to get even more solutions. In general, for any homogeneous linear differential equation, sums of solutions are also solutions, and also scalar multiples of solutions are also solutions. In fact, this is ultimately building up to the idea of linear combinations. We've got C1 times this whole thing, let's call that x1, plus C2 times this whole thing we would call x2. So we're using these two specific solutions, x1 and x2, linear combinations of those form the general solution. So in general, you can find the general solution of the differential equation, or rather the system of differential equations, by finding all linear combinations of the individual solutions we just found. So this then is our general solution. C1 times a vector function we're going to call x1 plus C2 times a vector function we're going to call x2. You could also even combine them into just one big vector. If you look at just the top component, we've got C1 e to the t times 1 plus C2 e to the negative t times 1. And then the bottom coordinate, you've got C1 e to the t times 1 plus C2 e to the negative t times 3. So 3 C2 e to the negative t. So if you look at this in terms of parametric equations, you could say x as a function of t is the top coordinate, and y as a function of t is the bottom coordinate. So if you wanted to graph this, if you've got a graphing calculator that will do parametric equations, you could just pick a value for C1 and pick a value for C2, type these in with those C1 and C2 values, hit graph, and you'll see one of the possible sample solution curves. Try different values for C1 and C2, and you'll see a variety of different solutions. Any questions on that general solution so far? Also, if we wanted a specific solution, what other information would you need to find C1 and C2? Yeah, initial conditions, initial values. And the initial conditions in this sort of situation would generally be like when t is 0, x is some vector, maybe like 5, -2, for instance. That just tells you a starting location. If you imagine this as a description of a point moving around in two-dimensional space as time passes, the initial condition would be, where is that point at time 0? Where is that object at the start of the experiment? So you could fill that in, replace every t with 0, you just get C1 times 1, 1 plus C2 times 1, 3 equals 5, -2. Solve that system of equations with linear algebra to find C1 and C2. Typically by setting that up as a system of equations and using row reduction or an inverse matrix to find C1 and C2. So that would give you a specific solution. Any other questions on that so far? Then let's also take a look at what the graph of this would resemble. Going back to that idea of the phase plane, but getting more detail. If we go back to this phase plane idea, an XY graph, if we take a look at the individual pieces of this, because remember, C1 and C2 could be any values. What would probably be the easiest values to use for C1 and C2? Even easier than 1 and 2. If we want to make this as simple as possible. Even simpler than making them both 1. What would be a number even easier than 1 to use here? They just make something drop out completely. Yeah, let's try 0. If we make C1 and C2 both 0, because remember, C1 and C2 could be any real numbers, including 0. If C1 and C2 both happen to be 0, what's our solution? Yeah, x equals the 0 vector is a solution. That would just mean we start off at the origin and we stay there forever. That's the equilibrium we saw when we were looking at the phase plane in the first place. If the initial condition is the 0, 0 vector, the origin, then that means the solution is just the 0 vector. It stays at the origin forever. If we're anywhere else, though, we're going to be going somewhere else. It's going to be a point in motion. For example, let's say we take a look at non-zero values. Maybe we make one of them 0, but the other one non-zero. So for instance, if C1 is 1 and C2 is 0, then the x vector is just 1 e to the t times 1, 1. If we consider that vector, 1, 1 is 1 to the right, 1 up. So that means we're at this point. But what's going to happen to 1, 1 as t gets larger and larger? Like, let's say we, instead of having 1 times 1, 1, let's say we have e to the 1 or e to the 2 or e to the 3. What happens to this vector as t gets larger and larger? Yeah, it's going to grow exponentially. Specifically, the magnitude is going to grow exponentially, but it's still in the 1, 1 direction because it's still a scalar, just a larger and larger scalar times 1, 1. So it's still in the 1, 1 direction, but it's growing larger and larger and larger, which means that that point is going to be moving along this line outwards to infinity. So that means one of the solution curves is a straight line in the 1, 1 direction, going outwards from the origin. Or alternatively, C1 could be -1. In that case, we'd have negative e to the t times 1, 1, which just means in the other direction, -1, -1. If we start there, we're going to keep going further and further out because this is still growing exponentially away from the origin, just in the -1, -1 direction. So this is another of these solutions. Growing exponentially towards infinity on the -1, -1 direction. But what about in the other direction? Let's say instead of making C1 1 or -1 and C2 0, let's go the other way around. Let's make C1 0, so this term is gone, and C2 is 1. Now we'd have x equals nothing plus 1 e to the -t times 1, 3. Our initial condition is going to be when t is 0, so that's 1 times 1, 3. So 1, 3. But what happens to this as t gets larger and larger? If you've got like 1, 3 times e to the -1, or 1, 3 times e to the -2, 1, 3 times e to the -10, 1, 3 times e to the -1,000,000. What's happening to e to more and more negative powers? Yeah, that's getting smaller. That's decaying towards what final value or what asymptote? Right. So we eventually get closer and closer to 0 times 1, 3. It's still going to be a vector in the 1, 3 direction, but it's going to get smaller and smaller. So that vector gets closer and closer to the origin. In other words, this point is going to be moving towards the origin along the line 1, 3. So the trajectory is going to be a straight line with slope 3, a straight line in the 1, 3 direction, but it's going to be going inwards towards the origin instead of away from the origin. We get exponential decay along this line, approaching very fast and then slower and slower and slower, getting closer and closer to the origin, but never actually getting there. Alternatively, we could have C1 be 0 and C2 be a negative number. In that case, the negative would distribute. So we get -1, -3, -1, -3, that's down here. But again, with the exponential decay, it's getting closer and closer and closer to the origin. So we're going to have another trajectory that's approaching along this line. Still going to be exponential decay in the sense that it's going fast and then gets slower and slower and slower, approaching the origin along that line. So these are essentially the two most fundamental solutions, the two most important solutions here. We've got approaching 0 along this line or diverging away from 0 along this line. So the two eigenvectors define two lines of either convergence or divergence. And why is it that along the 1, 3 line, everything's going towards the origin versus along the 1, 1 line, everything's diverging away from the origin? What made that difference? Why do we get such similar yet different behavior? Right, the eigenvalue. Along the 1, 3 line, everything is converging towards the origin because that was associated with a negative eigenvalue. Along the 1, 1 line, everything is diverging away from the origin because that was associated with a positive eigenvalue, exponential growth along a line versus exponential decay along a line. So for these two lines, any initial condition, not just leading to 0, 1 or 0, -1, any initial condition along one of these lines is going to lead to either C1 being 0 and C2 being something else, or C2 being 0 and C1 being something else. So we're going to get exponential decay towards the origin along one line, exponential growth away from the origin along the other line. What kind of equilibrium does that kind of act like? If we've got some solutions that approach equilibrium and others that diverge away from it, what were we calling that back at the beginning of the quarter? If it kind of looks stable from one direction, but unstable from another direction. Yeah, in one dimension, if we were just dealing with one function of one variable, we call that semi-stable. But yeah, in 2 dimensions, if we've got an x function and a y function, we usually call this a saddle point. And the reason we call this a saddle point is if we take a look at the other solution curves, like let's say instead of being on one of these lines, let's say you're a little bit off one of these lines. Let's say you start here. If you start here, your closest solution, your closest easy solution says converge towards equilibrium. So you're going to start converging towards equilibrium, but then you get kind of closer to this other solution. So the exponential growth starts to play a role, and you start diverging out this direction instead. So one of the solutions is going to look like this. Starts off kind of converging towards the equilibrium, but then ends up diverging instead. Or something like this. And these are the sorts of curves we were seeing from the phase plane as well. When we were drawing out the phase plane, we ended up with some curves that were going upwards steeply through the y-axis and then upwards somewhat less steeply through the x-axis and curving out like this. Or we had some others that were curving steeply downwards like this and then curving more towards this. So these other curves are a combination of exponential growth in one direction and exponential decay in the other direction. But if you're adding something that gets bigger and bigger plus something that gets closer and closer to 0, what would those add up to? What do you get if you add a very large number plus a number close to 0? Yeah, you get the large number because the number that's getting closer and closer to 0 ultimately doesn't matter so much. The exponential growth term dominates over the exponential decay term because the exponential decay term is approaching 0. So that means all of these solutions, or at least almost all of them, will look like exponential growth towards infinity. The only ones that end up with actually decaying towards zero are the ones where C1 happens to be zero. Those are just the ones converging along this single line. So any solution that involves an initial condition on this line with slope 3, those are actually going to converge towards the origin. Everything else is going to diverge off to infinity. Even these in-between values here, these end up, like if you start here, you kind of start converging, but then you swivel around really quickly and diverge off to infinity instead. Or if you start here, you start converging, but then you change your mind and diverge instead. And the reason this is called a saddle point at the origin is if you imagine these as elevation curves, like if you had a mountain range that had altitude curves that look kind of like this, then ultimately that's going to end up looking sort of kind of shaped like a saddle in the sense that you've got like a single point that goes down in two directions, but goes up in the other directions. So I think it's a hyperboloid shape, mathematically speaking, but it ends up looking kind of like a saddle. And so we call this a saddle point. This, of course, doesn't actually represent the elevation curves. It represents possible trajectories of objects moving along these sorts of paths. But it resembles the elevation map of a saddle point. And so we typically call this a saddle point. But it is essentially the two-dimensional equivalent of a semi-stable equilibrium. Any other questions on that? Or the general idea of systems of differential equations? By the way, what would you expect to happen if you ended up with both of the eigenvalues being negative? If these were both negative, what would you expect to happen? If you've got like, if this is e to the negative t, and let's say this was e to the negative 2t, what would you expect those functions to do? It wouldn't quite be the opposite. Because if these are both negative, what are all the solutions going to do? Yeah, all the solutions are going to shrink towards zero, no matter which direction they're coming in from. They might be curved, depending on which one is which one is more negative. But if both of the eigenvalues are negative, all the solutions are going to converge towards zero. And that would be stable equilibrium, which we often call a sink, in the sense that it's like everything's sinking into this point. It's like a drain in a sink. Everything's converging towards that point. Whereas if they're both positive, what would you expect all of the solutions to be doing? If you had like e to the t times a vector and e to the 2t times a vector, what's going to happen there? Yeah, they're all going to diverge. Everything would be going outwards from the origin, sometimes in some curves, depending on which one is stronger, positive. Like you wouldn't have functions that come in somewhat and then diverge outwards. All of them are going to be just diverging outwards. But this would usually be called a source. Specifically, the origin would be called a source point. And that's the equivalent of unstable equilibrium, where everything's diverging away from it. Except if you start off at the origin exactly, you would stay there forever. Zero is still a solution. So if you're at the equilibrium point, you'll stay there forever. But if you're even a little bit away from it, you're going to diverge out to infinity. So that would be called a sink, which is the equivalent of stable equilibrium, or a source, which is the equivalent of unstable equilibrium. And then a saddle point is very much like semi-stable equilibrium. So those would be the equivalents of those for the two-dimensional system. Those aren't the only options though, because we have like maybe both of the eigenvalues are positive, or maybe they're both negative, or you've got one positive and one negative. But what else could they be other than real numbers? What's another possibility for the eigenvalues when you're solving it using a quadratic? Yeah, they might be complex conjugates. You might have imaginary parts. And if you've got e to a complex power, yeah, if you have e to an imaginary power, what sort of function does that turn into? What else could be happening there if you have e to an imaginary power? What sort of behavior does that lead to? Yeah, that ends up being sine and cosine. So another possibility, if you have imaginary lambdas, specifically, let's assume that they are pure imaginary. If you have, like, let's say e to the 5it and e to the negative 5it, those become just sine and cosine. And that means that if you consider both the top coordinate as x and the bottom coordinate as y, those are both sinusoidal. They're both oscillators. So x is oscillating as time passes, and y is also oscillating as time passes. What would be a trajectory where the x coordinate oscillates back and forth and the y coordinate oscillates back and forth? Like if you just take a pen, a marker, or a pencil or whatever, and you're wiggling side to side and wiggling up and down. If you're going side to side and up and down, what sort of shape are you tracing out? Yeah, a circle or possibly some sort of ellipse or oval. So that sort of situation, since you're oscillating side to side and up and down, depending on exactly what the amplitudes and frequencies are, you're going to end up with some sort of elliptical shape. Unless you're at the origin. If you're at the origin, of course, you'll just stay there forever. But if you're some distance away from the origin, you're going to end up with sort of this repeating oval shape with the exact direction depending on the coordinates of the vectors. But you're going to end up with presumably infinitely many possible oval shapes, all circling around centered at the origin. In that case, we typically call the origin an orbit point, in the sense that everything's orbiting around that point. Or if it's not pure imaginary, but if it's a complex number, if you've got eigenvalues that have a mixture of real and imaginary terms, if you've got e to the power of something real and something imaginary, typically we'd split that up into e to the real part and e to the imaginary part. The imaginary part's going to turn into sines and cosines, but we still have e to a real power. So we end up with oscillator times exponential growth or decay. What would that look like if your x and y coordinates are oscillating, but also you've got exponential growth or decay going on? What would that look like? If you've got an oscillator, but you're multiplying it by something that's getting larger and larger or smaller and smaller. Yeah, you're going to end up with a spiral. You're still circling around the origin, but if you're circling around and getting larger and larger, you're spiraling outwards. Or you could be circling around and getting smaller and smaller, spiraling inwards towards the origin. So those are also possibilities. If you've got complex lambdas, a mixture of real and imaginary, but of course they're going to have to be complex conjugates, then you can end up with a spiral. And it might be spiraling outwards from the origin, or it might be spiraling inwards towards the origin, depending on the direction. Actually, that ultimately depends on the real part. If the real part is positive, then you get e to a positive power times t, and that'll be exponential growth. If the real part is negative, you get e to a negative power times t, and that'll be exponential decay. Either way, the origin would be called a spiral point, in the sense that it's spiraling around that. Might be spiraling inwards, might be spiraling outwards, depending on whether the real part of the complex conjugate roots is positive or negative. But those are the main possibilities there. You could have the lambda values be a mixture of positive and negative, or maybe they're all negative or all positive. Maybe you've got pure imaginary values and you just oscillate around, or maybe you've got mixed complex values and you spiral inwards or outwards. But those are the main possible results. Any other questions on that? Or systems of differential equations in general? Outwards would be, if you're getting further and further, that's going to happen if the real part is positive, because then you'd have e to a positive number times t, which means it's expanding larger and larger, exponential growth. But if the real part is negative, then it's going to behave like this. Everything's getting closer and closer to the origin as it oscillates. So it's going to be spiraling inwards, closer and closer to the origin. So whether it's spiraling outwards or inwards depends entirely on whether the real part of the eigenvalues is positive or negative. And then the imaginary part determines things like how fast it's oscillating. How many, I guess you might say, how many oscillations, how many cycles per second. Any other questions on that? All right, I'm going to take off and get ready for my next review session, but keep trying those practice problems. Let me know if you have any other questions. Good luck on finals and have a nice break. See you around. You're welcome.